Lecture 7-2, The Nature of Earthquakes. Now, an earthquake is defined as the shaking and trembling that results from the movement of rocks beneath their surface. There's a break that occurs deep underground. It causes vibrations to travel outwards from there. That's the earthquake. Now, why do earthquakes happen? Well, that's where the elastic rebound theory comes into play. It's when stresses cause strain to build up. Now, stresses are kind of forces. So the compression, the tension, the shearing forces, they cause strain to build up in rocks until they can no longer bend elastically. Remember, elastically is where it could bend, and then if the force was released, it could bounce back to its original shape and size. Once they can no longer bend elastically and they break, that's what's going to cause the earthquake. So you see in this animation here, you can see that this is getting kind of pushed that way, this side is getting pushed that way, and then right here is our fault. And so the strain is building, and then you see the big break, and when that break happens, vibrations will be sent outwards in all directions, and that is our earthquake. So elastic rebound theory helps explain why earthquakes happen. Stresses build up until they can no longer take it. For the break, the movement happens, and then the vibrations are sent outwards in all directions. Now, when we talk about earthquake, two terms you're going to hear a lot are focus and epicenter. And they're both talking about where does the earthquake start. The focus is deep underground. Now, that's where the earthquake happens. We always talk about the depth of an earthquake. Earthquakes don't happen really on the surface. They happen underground, sometimes very, very deep, sometimes very shallow, but they always happen underground. So the focus is the area under the surface where rock breaks, triggering the earthquake. The epicenter is a spot directly above the focus on the Earth's surface. So when we measure how far away was an earthquake from us, we measure from the epicenter because we measure from on the surface. Typically, how deep an earthquake occurs will greatly impact the amount of damage caused by that earthquake. It also depends on location, but depth plays a big role. So focus is where the break happens deep underground, the earthquake starts. Epicenter is a spot directly above it on the surface. And then you can see these little circles here are called wave fronts. That just means that the waves, the vibrations, travel outwards. Now, an earthquake is kind of like sound, but sound that passes through the earth. It's a vibration. They behave very much the same way. Now, when an earthquake happens, it produces three different types of seismic waves. So three different types of vibrations that travel outwards in all directions. The first kind is called the P wave, and it's called this because it's the primary wave. It travels the fastest through the ground. It can go through liquids and solids, and it's going to be the first thing that our seismograph can record because it's going to be traveling the fastest. It'll get to us the quickest. The S wave is called the S wave because it's a secondary wave. It travels a little slower than the primary wave. It does not pass through liquids, so it can't pass through oceans. It can't pass through the outer core of the Earth. Remember, the outer core of the Earth is liquid, so a P wave can pass through that, an S wave can't. And it's because they're different types of vibrations. A P wave is more of a compression wave. Now, I know this graphic may be a little hard to see, but what happens is that this is the part of the Earth we're talking about. It vibrates back and forth while the wave travels outwards. So it vibrates in the same direction that the earthquake moves. And so it causes parts of the Earth to get compressed, some parts to stretch out, and then compressed, stretched out, compressed. And that's kind of how it moves. Think about if you held a slinky straight out, you compress part of it and just let go, you'll see it kind of bounce back and forth in the direction it moves. An S wave is more what you think about with a wave. If this is the part of the S wave we're talking about here, it moves up and down while the vibration moves left to right. Now, this is what you can think about like a water wave. That would be more similar to an S wave. So there's two very different types of vibrations here. And that's why a P wave can pass through liquids, but an S wave can't. And that's why an S wave is also slower. Now, the L wave moves a lot like the S wave, but this is on the surface. Now, the L actually stands for love. It's called the love wave, named after a scientist. It has nothing to do with emotions or anything like that. This is what happens on the surface. Now, this is the most destructive because this is, well, of course, we're talking about buildings that occur on the surface, and this can actually cause the surface to move up and down like a water wave. You can actually see that flowing up and down. This is going to be the slowest wave. It'll be the last one we record, but it's oftentimes going to be the most powerful that we record. It's easy to see this on a seismograph reading. So 3 different types of seismic waves. P wave, the primary wave, compression. S wave is more up and down, what we tend to call transverse. L wave is what happens on the surface. Now this little graphic here, you can see the S waves will only travel through a solid, so the outer core here, the S waves can't pass through. And so there's a big blind spot on the other side of the Earth from when the earthquake happens because the S wave could not pass through the outer core. The P waves can, but as the P wave travels from different density materials, it's going to bend. It's the same reason why if you've ever been outside at a lake at night, you can hear sound from all the way across the lake, and that's because the heat from the water actually causes all the sound to bend, and so the sound kind of curves up away from the water, and so you can hear from much farther away. P waves travel through the Earth. They're refracted or bent. Here we go. Bent when they pass through a medium. The paths of these waves are curved because density is gradually changing. And so that tells us, again, we go back to when we talk about the structure of the Earth, this is how we understand the different densities that make up the Earth and how we can identify what makes up each section. Now, one of the effects of a vibration earthquake that happens on the ocean floor is a tsunami. A tsunami is devastating waves usually caused by undersea earthquakes or other large shocks. What typically happens is that you can see here is that part of the ocean floor goes up while part of it goes down. That's our break. That's our fault line right here where the earthquake happens. And when that shift happens, it pushes some water up. And that's a lot of water deep in the ocean. And so this wave will get pushed out from there. Now, in deep water of the ocean, the height of the wave is very, very low in the open ocean because it's a lot of water at that point, so it doesn't have to change by a lot. But when the coastline, when the shoreline goes up, that wave is going to go higher and higher and higher. And so a wave that in deep water may only look like that here, it's off the charts at that point. Just a giant wave because it's getting pushed up by the bottom. Here's a little animation showing you what typically can happen. This is the Sumatra earthquake, which caused a very devastating tsunami. You can see right in here, this is where our motion is happening. So the 2 plates are meeting, and it's, there's elastic rebound theory again, where you can see that all that stress built up and then it was released. Okay, we'll watch this one more time. So we get that stress happening here. Strain builds until there's going to be release of it, a break. So the earthquake happens. This land moves suddenly, and that causes the giant wave to happen. And so this happens anytime there's a major earthquake along a fault line in the ocean. We always look for a tsunami. A tsunami is not something easy to spot in the open ocean, but is much easier to spot once it gets closer to shore. Now, of course, tsunamis occur in certain regions of the world because of where our plate boundaries are. This is a recent picture taken of the major earthquakes in the world within the last week, and you can easily see that I can connect the dots here. And we talked about the Pacific Ring of Fire before, but there are, of course, at major plate boundaries, that's where earthquakes are more likely to happen. Places like here in Hawaii, this is what we call a hotspot volcano. It does not happen anywhere near a plate boundary. It happens far away, and so the same process that forms a volcano out there also causes those earthquakes to happen. And so not all earthquakes happen at plate boundaries. Some of them happen far away, depending on if there's a weakness in the crust, like here in the hotspot, or if there's other weakness causing motion in the crust at that point. And so we have major earthquake regions. So you see most of these places, most of these earthquakes that you see are very common. Alaska here gets a ton of earthquakes each year. The western coast of South America is constantly bombarded with earthquakes. Then, of course, if you go through Japan, it's pretty much an island nation that deals with earthquakes all the time. And then you look anywhere along the Pacific plate. In the United States, we do have some regions that have higher earthquake hazards than others. And of course, here we are in Iowa. Our nearest one that we worry about is right down here. This is called the New Madrid Fault Zone. Now, it is responsible for a lot of earthquake activity. It was also responsible for major earthquake activity a long time ago in the 1800s. It was so powerful of an earthquake, it actually caused the Mississippi River to flow backwards. And so this is a major region that we can see a couple earthquakes happen here every week, but this is where we also can expect a very large earthquake someday down the road. Now, of course, on the west coast, you look where we have a lot of mountainous regions because of the same process form mountains also will cause earthquakes to happen. So on the western coast here, of course, in California, and don't forget the name of the major fault line in California is the San Andreas fault line, and it happens right here. We have a lot of people that are close to that fault line that could be very much impacted. This area here is Yellowstone National Park, site of another hotspot similar to Hawaii, but this is also home to a supervolcano, which is a very large volcano that could erupt someday and actually send ash into Iowa. Now you can see we have just a slight risk here in Oklahoma. We have a couple of those. We measured one earlier this year from that. You look anywhere in the west half of the United States because of the plate boundaries that happen there. And then here in South Carolina even, there's a risk there. Charleston's been hit by major earthquakes in the past. If they were to get hit by another major earthquake, there'd be a tremendous amount of damage and loss of life. Now, of course, Alaska is at a convergent plate boundary. Tons of earthquakes happen here every week. We have volcanoes that are active all the time. A lot of mountain formation there. So Alaska is another major earthquake zone. So we do have places in the United States where a lot of earthquakes, and of course, you look at Iowa, and we're pretty much void of that. We haven't had major earthquakes in Iowa since people have settled it.